Chernobyl, Reactor 4, April 1986. For a long time, nothing unusual appears to be happening inside the reactor, and that absence of urgency is precisely what allows everything else to continue without resistance. The reactor does not shut down, it does not trigger alarms, and it does not demand attention in any obvious or dramatic way, which means that every signal the operators see reinforces the same quiet conclusion. The system is still functioning. Lights remain on across the control panels, indicators continue to move within expected ranges, and numbers update steadily, creating a visual rhythm that suggests activity without danger. The test is running, and because it is running, it carries with it an unspoken assumption that it should keep running unless something clearly forces it to stop. Nothing does. There is no single moment that demands a decision, no sharp warning that interrupts routine, and no visible threshold that signals risk. Only a continuous flow of small confirmations that suggest the situation remains manageable. When no moment forces a decision, continuation becomes the default, not because it is evaluated as safer, but because interrupting requires effort, justification, and explanation that the system does not naturally reward. This is not chaos, it is order. You already know how this story ends, and that familiarity creates a misleading sense that the outcome must have been obvious to those inside the room, as if the conclusion were written clearly into the early moments. It was not. What matters happens earlier, long before the world begins paying attention, at a time when everything still appears stable enough to justify patience and restraint. This is the part that rarely gets examined, because nothing visible seems to be going wrong yet. The control room is calm, voices are low, procedures are being followed, and the environment feels routine rather than dangerous, which is important, because urgency is usually what interrupts momentum. Here, there is none. And without urgency, systems tend to keep moving forward on their own. The test itself is not dramatic, and it is not designed to push the reactor toward failure, which is why it rarely attracts much attention when described in isolation. It is not secret, it is not experimental, and it does not involve unknown technology or untested procedures, but instead exists as a routine administrative requirement that had been left unresolved for reasons that were always practical rather than technical. The purpose of the test is narrow and specific: to determine whether the reactor could generate enough residual electrical power after a shutdown to keep essential systems running during the brief interval before backup generators fully engaged. On paper, it is a question of timing, margins, and redundancy, not of danger. This kind of test rarely feels urgent, not because it lacks importance, but because it can always be postponed in favor of more immediate operational demands, and at Chernobyl, that is exactly what had happened more than once. Grid requirements changed, schedules shifted, other priorities intervened, and each postponement felt reasonable on its own, especially because the reactor itself continued operating without issue. Over time, the test became something that existed in the background, acknowledged but deferred, waiting for a moment when conditions would finally align well enough to justify proceeding. That moment arrives on the night of April 26th, not because conditions are ideal, but because they are acceptable, and acceptable often feels sufficient when a task has been waiting for too long. The reactor has been running for hours. The system is warm, predictable, and familiar to the operators, and there is no particular reason to expect a sudden or uncontrollable deviation from normal behavior. Expectation shapes attention, and attention determines what people notice, which means that when nothing seems likely to go wrong, subtle signals become easier to dismiss. Power reduction begins as part of the preparation for the test, and at first it follows a familiar and controlled trajectory that does not raise immediate concern among those monitoring the reactor. However, the power level drops lower than planned and then lower than expected, creating a situation that is not classified as dangerous but inconvenient, because the reactor is no longer operating within the narrow range that makes control effortless. This is not treated as a failure. The reactor remains active, stable, and responsive, which means that corrective options are available and permitted under existing procedures, reinforcing the idea that the situation can still be managed internally without escalation. Control rods are withdrawn to compensate for the loss of power, a standard corrective action that has been performed before, documented before, and successfully resolved similar conditions in the past. The system responds not smoothly and not elegantly, but sufficiently enough to confirm that the adjustment has produced the desired effect in the short term. This confirmation matters because each successful response strengthens the belief that the system remains under control, even as its configuration begins to drift further from its original design assumptions. Every correction solves an immediate problem, but each solution subtly alters the state of the reactor, introducing new dependencies that must also be monitored and managed, often without being fully understood as part of a larger pattern. Nothing collapses. No alarms demand attention. And because nothing visibly fails, the growing complexity of the system remains largely invisible to those inside the control room. This is how risk accumulates in operational environments, not through dramatic mistakes, but through a sequence of reasonable actions whose combined effects are difficult to perceive in real time. As the test continues, time begins to play a quiet but significant role, not by introducing urgency, but by normalizing the conditions that have already been created. Hours pass, and with them come shift changes, handovers, and subtle transfers of responsibility that alter how decisions are perceived and evaluated. The operators now entering the control room did not initiate the test, and they did not make the early adjustments that shaped the reactor's current state, but they inherit a system that is already in motion and an expectation that the process will be completed. Inherited decisions carry a different psychological weight than original ones, because stopping something you did not start requires questioning the judgment of others, introducing doubt where none has yet been formally expressed. Stopping now would require explanation, documentation, and justification, all of which impose immediate social and procedural costs, while continuing requires no such effort and appears on the surface to preserve stability. Fatigue does not manifest as confusion or panic, but as a narrowing of focus, where attention becomes centered on keeping the process moving rather than re-evaluating its broader implications. Each operator sees only a fragment of the system, a set of indicators and parameters that suggest local control. even as the global state of the reactor becomes increasingly complex. The absence of a clear failure reinforces the belief that the situation remains contained, and containment, even if imperfect, often feels preferable to interruption. No single person in the control room sees the entire system, and no single display reflects the full consequences of the adjustments that have accumulated over time. Each panel reports stability within its own scope. Each instrument confirms that its assigned function remains operational, and together they create a fragmented picture that suggests control without revealing vulnerability. The reactor does not appear dangerous. It appears busy, active, and responsive, which is often more reassuring than genuine simplicity because complexity can be mistaken for capability. As conditions continue to drift further from the reactor's original design parameters, automatic safety systems begin to interfere, not because they detect imminent failure, but because the system is operating in a region where protective mechanisms become inconvenient. These systems are not broken, and they are not disabled recklessly, but overridden in accordance with procedures that exist precisely to allow flexibility under unusual but manageable circumstances. Each override feels justified in isolation, and each adjustment preserves the illusion that control remains distributed and intact. What no one fully recognizes is that the reactor is now operating in a configuration that no single document describes and no single individual fully understands, making its behavior increasingly dependent on physical processes rather than human intention. When the final phase of the test begins, there is still no visible sense that the system has crossed into a fundamentally different state. The procedures being followed are familiar, the sequence of actions appears logical, and the operators are responding to conditions that, on their own, do not signal catastrophe. What has changed is not the intention behind the actions, but the context in which they are occurring. A context shaped by hours of accumulated adjustments that have quietly altered how the reactor behaves. When the reactor finally reacts, it does not respond to a single command or mistake, but to the combined state created by everything that has come before it. Control is lost faster than it can be recognized, not because the operators hesitate, but because the system transitions from a domain governed by procedure into one governed by physics. Inputs no longer produce predictable outputs, and the feedback loops that once allowed correction now amplify instability. At this point, there is no meaningful opportunity to reconsider, interrupt, or reverse what has already been set in motion, because the conditions that made continuation feel manageable have already passed. What follows happens quickly, and the details are well known, but they are not where the story truly turns. The explosion, the fire, and the immediate response draw attention because they are visible, dramatic, and irreversible. But they occur after the decisive shift has already taken place. The reactor is no longer something that can be managed or corrected, and the consequences that unfold over days, months, and years are reactions to a condition that has already been locked in. Chernobyl is remembered for the moment the world noticed, but the situation changed earlier, during a period when everything still appeared controlled enough to justify patience and restraint. The most important decisions did not announce themselves as decisions at all. They arrived as continuations, as reasonable responses to local problems, and as choices that felt smaller than stopping. This is why events like this are difficult to recognize in real time, because the point at which outcomes become inevitable rarely coincides with the moment when consequences become visible. By the time the story becomes obvious, the conditions that shaped it have already disappeared.